last section we talked about the degree of a vertex, and now we extend that idea to look at the degree sequence of a graph. So if a graph G has the vertices v1 through vn, then we say that the degree sequence of the graph is just an ordered list of the degrees of all the vertices, right? So delta G of v1 just means the degree of v1, delta G of v2 is the degree of v2, etc. And remember, degree just means the number of edges that are incident with that vertex. Conventionally, we just list the sequence in non-increasing order. In other words, from big to small. So if we looked at this graph here, we could go through and find the degree of each vertex. So this is degree 2, degree 1, 2, 3, 4, 1, 1, 1, 1, and 0. And conventionally, we list this degree sequence in decreasing order. So I would write it as, my biggest one would be 4, then 2 again. Then we have 1, 1, 1, 1, and finally 0. Okay, so remember what we learned last time, which is that if you were to add up the degrees of all the vertices in the graph, every single edge is going to get accounted for twice, which means you should get 2 times the number of edges, 2 times the size of the graph. And we can check that that's true here. If we were to add up all the degrees, in other words, add up all the entries in the degree sequence, we'd have 4, 6, 8, 9, 10, 11, 12. And if we were to add up all the edges, we'd have 1, 2, 3, 4, 5, 6. So 2 times 6, 2 times the number of edges, gives you the sum of the degrees, right? Or the sum of the entries in the degree sequence. And we can use that to prove a result about whether or not a particular sequence could be the degree sequence for a graph. So if we let d1 through dn be some sequence of non-negative integers, and if we know that when you add up all of the degrees, right, if you add up all the entries in this degree, or I shouldn't call it a degree sequence because it's not necessarily for a graph yet, but if you add up all the entries in this sequence and you get a sum that is odd, well then it couldn't possibly be the degree sequence of a graph, right? Then this cannot be the degree sequence of any graph. All right, so let's try to prove that. And to prove it, I'm going to use a theorem that we talked about in the last section, theorem 1.5.1, and let's try to prove this by contradiction. So let's assume, by way of contradiction, I'm just going to shorten by way of contradiction for the sake of not having to write it all. Assume by way of contradiction that this sequence of numbers does describe the degrees of some graph G. So suppose it is the degree sequence for some graph G. What that means is that D1 is going to have to be the degree of some vertex V1 in the graph, D2 is going to have to be the vertex, or the degree of some vertex V2, etc. And so when we take this sum over all of these di entries, where I is going from 1 to n, it's the same thing as adding up all the degrees of all the vertices in the graph. This is the same as the sum of all the vertices, the degrees of all the vertices in the graph. Now, we know from our assumption here that this sum has to be odd, which means we can express it as 2k plus 1 for some integer k. But we also know that this is going to be equal to 2 times epsilon, where epsilon represents the size of the graph. And we know this is true by theorem 1.5.1 from last time. Okay? Well, 2 times epsilon is 2 times an integer, which means this sum is even, but it's equal to 2k plus 1, which is odd. Right? An even cannot be equal to an odd. So since this sum cannot be both even and odd, we've reached a contradiction. And so this can't actually be the degree sequence of any graph. So D1 through Dn is not a degree sequence for any graph. Okay. All right, so why do we care about this? Why is this useful? Well, sometimes someone might hand you a list of integers and ask you to build a graph that has that property. And maybe such a graph doesn't exist. This is just one sort of quick way to check. A good question to ask yourself is this an if and only if? In other words, if somebody hands you a sequence of integers and the sum of those integers happens to be even, does that mean that there's definitely going to be a graph that has that degree sequence? That's something that you'll explore in the exercises. Okay, but we also want to recall that in a simple graph G, we know that for a simple graph, the degree of a vertex is going to be between 0 and n minus 1, right? We talked about that in the last section as well. And so if we knew that D1 through Dn is the degree sequence of a simple graph, then we should know that, okay, assume that this is written in non-increasing order. That means that this is sort of your largest possible degree. This is for your smallest possible degree. And so we have that D1 is going to be less than or equal to n minus 1, right? Because this is some degree in the graph. This is the largest possible one, which is greater than or equal to D2, greater than or equal to D3, all the way down to Dn, which has to be greater than or equal to 0. Okay, I sort of wrote this in a backwards way, but you get the idea. Okay, and so this is another useful thing. If you're handed a particular sequence of integers and you're trying to figure out if it's the degree sequence for a simple graph, well, make sure first of all that your first entry, it can't be bigger than n minus 1. And your last entry can't be bigger than 0. Okay, that's kind of silly. It's meaningless if you had a negative number there. But it's just one more sort of technique that we have to try to help figure out whether a graph exists with a particular degree sequence or not.